We're going to do a review today using this review document, which I'm pretty sure is the one. Let's see if it's the one I gave you. Yeah, looks like it. Okay, so no tricks today. That is the review document. And this is probably not going to work. Shut it off. Let's see, how many business? No, not until we do the lab. All right, so let's get through chapter 13. And right one. Looks like it. Number one. Which of the following statements about the equilibrium is false? So they're referencing this particular equation. Hydrogen gas plus iodine solid, I believe, is in equilibrium with hydrogen iodide gas. All right. So we're looking for the false statement. If the system is heated, the right side is favored. Now, based on what we covered 2 days ago, there's no way to tell. Right? Not based upon exothermic, endothermic. So we have to make some assumptions in order to determine whether this is true or false. System is heated, the right side is favored. If what type of equation, what type of reaction do we think this is? If it's hydrogen gas and iodine solid, we have to break a bond here. We have to break a bond here, and we get 2 bonds back here. Right. Nothing comes to mind. So let me look, see what I deduced when I wrote this document. All right. The way I approached it in the worked problems was that if we add heat to this side, what's that going to do to the reaction rates? Well, we're going to increase the kinetic energy of this one and that one. So when they collide, they're more likely to have a reaction. Which would do what to the reaction rates? Well, if we think of them in terms of their constants, the reaction rate constant, then if we increase heat on this side, we're going to increase the rate here. Right? And that's telling us that the right-hand side is favored. Although that's not a good question. Anybody think that's a good question? No, that's not a good question. We're assuming then, based upon that model, that the statement is true. The right side would be favored. But if we look up the enthalpy for this reaction, then it may completely contradict that statement. That's the one possibility. Right? And I didn't look it up. All right, so if this type of a question shows up in an exam, then you could argue one way or the other. If we're saying that this one is true, and then let's put a question mark there, just in case. This is a heterogeneous equilibrium. Okay, we can answer that one. Right? You've got a phase, gas phase here and a solid phase here. So yeah, it is heterogeneous. That was easy. Should have started with B. If pressure on the system is increased by changing volume, the left side is favored. Okay, so here, what do we compare? We compare the moles of gas in the balanced equation. On this side, we have 2 moles. On this side, we have 1. Okay. So how does the system respond when we increase the pressure by decreasing the volume? It tries to make fewer moles, because fewer moles, according to Avogadro, will reduce the pressure. It will relieve that stress. So the shift will be to the left if we increase the pressure. That means C is true. Adding more hydrogen increases the equilibrium constant. Does that change the equilibrium constant? No, it changes the equilibrium position, right? Le Chatelier kicks in. But when you change the concentration of any of the components, then that has no effect on the equilibrium constant because it's only dependent on temperature. Well, the only thing we can change in this situation is temperature. That will change the constant, right? Other factors that determine the constant, right? The reaction mechanism, right, will determine the constant. But that's not something we can change. But temperature, yeah. If we change the temperature, we can change the constant, but changing the concentration of one of the reactants or products has no effect on the K at all. It's a constant at a given temperature. So the last one is probably true also. Removing HI as it forms forces the equilibrium to the right. That's true. When you remove this, then there are fewer of these to go reverse. Right? So this reaction rate, what remains unchanged, and this reaction rate decreases. So in order to get them back into balance, we need more of this. So this one is going to dominate until we have enough of this to balance that one against the forward reaction. So the reaction is going to shift to the right in terms of concentration. So the equilibrium position shifts to the right. And that was true. Okay. So this is the only squirrely one in there that really doesn't have a good explanation. I tried to explain it there, but I don't even like my explanation. Just, we need to know what's the enthalpy of this reaction in order to answer this one definitively. Now, if this is true, if it does shift to the right, what type of a reaction is this, endothermic or exothermic? If you increase the temperature, it would have to be endothermic because we're adding this component that drives it to the right. So if we knew that it were endothermic, that would be a no-brainer. But if we find out it's exothermic, then this explanation is just all wet. Okay, see what I'm getting at? Yeah. All right, how about number 2? I'm gonna have to do this manually. Let's see, do I have room? No, I don't have room for 3. So we'll just stay with 2. Which of the following is true for a system whose equilibrium constant is relatively small? So if you have a constant here, and you have products here, and reactants here, right? If this is a very small number, if K is much, much, much less than 1, okay, what does that say about the reaction? Does it have anything to say about the time it takes to reach equilibrium? No. Right? Equilibrium is only concerned with, right? Only concerned with this part and this part. How long it takes to get there is this part. That's kinetics. Right? And I should label my axes, or this is the progress of the reaction from left to right. So we studied this one in chapter 12. That's the rate of the reaction, how fast it gets there. But this one says which is favored. Like when we study this part of the diagram, we're talking about equilibrium. This part is kinetics. So A, you cannot deduce A from that statement. It'll take a long time to reach equilibrium. No, short time, long time, A and B are false. There's no way that they can say anything about that. For instance, diamond. We think of diamond as forever. Right? When you've got a diamond, it's going to be there. It's stable, chemically stable. It's not. In terms of equilibrium, diamond is very unstable. In other words, over time, it will degrade. It will just disappear. Oxidize, perhaps. But it's going to take a very long time to get there. And so equilibrium says it's not stable. It's not favored condition. But kinetics says it's going to take millions of years to reach that equilibrium. All right, so the equilibrium lies to the left. And if it's very small, that means this is very small, this is very big, relatively speaking. So the products, very small. The reactants are favored, right? Very large, very small, very large. So it is. The equilibrium lies to the left. And 3. Do some scrolling here. We're basing it on, yeah, I got everything there. Basing it on this equation, carbon dioxide and hydrogen. Yields what? Carbon monoxide and water. And we're saying water is vapor under these conditions. So all of these are gases. And the delta H, the enthalpy for this reaction is plus 42 kilojoules per mole. So just looking at what we've got so far, what type of reaction is that? Endothermic or exothermic? Endothermic. Exactly right. Plus means the heat, the enthalpy is on this side, goes into the reaction and is buried in the products. Okay, what else are we given? K equals 1.6. So K is given to us as 1.6 at a given temperature, 1260 K, at 1260 K. All right. So if 0.15 moles each of reactants and products, so we've got, let's see, walking all over my, there. So if initial concentrations are 0.15 molar for each one, okay, then what happens? That's moles per liter. Okay, so it is molar. That many moles per liter of each one are placed in a vessel, an insulated vessel at 1260 K. Then as the system came to equilibrium, the temperature, okay, we're saying something about the temperature and the mass of CO2. Look, based on the answers. What happens to the temperature? Increase or decrease? And what happens to the mass of CO2? And we can assume that since we're not changing volume, then if we know the concentration, we know the mass changes. So what happens to the mass of CO2? Okay. All right, so K says 1.6. Right. I started to write an ice table, but I don't think we need one. not to answer this question. K equals what? CO, is that balanced though? One carbon, two oxygens. Yep. Two hydrogens. Okay, it's balanced. So everything is to the first power. And then CO2 and H2. All right. So how do we know which way the reaction is going to go? With that information, our starting position is 0.15 molar on everything. Then we have to calculate Q, right? So each one of these is 0.15, right? So K equals 1, right? Okay. Excuse me. Q equals 1. So how does that compare to K? Well, if Q is less than K, what does that say? If Q is less than K, that means we don't have enough of this and we have too much of that. Correct? It's going to the right. Yeah, so it's going to go to the right. CO2 will decrease in mass. And if it's coming this direction, the temperature should increase, right? Because delta H is over here. If it goes this way, then the temperature should increase. Okay. So which one is well, it says temperature would decrease and mass would decrease.
Is that side is heated? So on the other side, that's not really cool, right?
Let's see. System cover. Oh, hold on a second. If K is greater than Q, Q is less than K. Okay, I was looking at it backwards. Q is less than K. So this is too small. This is too large. It's going to the right.
That's what I said.
Yeah, it's going to the right. Yeah, okay. So CO2 would decrease and temperature would also decrease because we're consuming heat as we go to the right. Yeah. Okay, so B is the right answer. Temperature decreases, CO2 decreases. Did I lose anybody? Okay. All right, that was 3. And looks like we're picking them up one at a time. Okay, we've got, get that out of my way. Come on. The system's misbehaving. 4 through 6 is based upon 2A yields 2B plus C. 2A plus 2B. C. And they're all gases. Okay. So 4, referencing that equation. Oh, at a temperature, at a particular temperature, K is equal to 1.6. 6 times 10 to the 4th. And we might as well put the equation in here because we might need it. So C is on top. A is squared and B is squared. Okay. Addition of B to the equilibrium mixture of the above will do what? If we add B, then it's going to consume some of the A and make more C. Right. So A is going to decrease. Addition of chemical B at equilibrium.
You have it written up there on.
Do
2A.
Oh, I'm sorry. Yeah, you're right. There we go. All right, that'll mean this has to change. There we go. That look better. Yeah. Okay. Now let's go back. Addition of B. All right, that's on the product side. So addition of B is going to drive it to the left and A is going to increase. All right, so that's true. A is the answer to that one. At a higher temperature, K equals 1.8 times 10 to the minus 5. So this is at T1, and at T2, we've got 1.8 times 10 to the minus 5. So now K has decreased considerably, and T2 is greater than T1. So we increase the temperature and we change the equilibrium to just the opposite. Instead of these factors, instead of the right-hand side products being favored, now the products are not favored. The reactant is favored. So if the reactant is favored, and we increase the temperature, would that mean it's exothermic? Right. You increase the temperature, we drive the equilibrium back this direction, where this is big and that's small. So that makes this very small. Does everybody follow me? I see one nodding hand, two nodding heads. Okay. One just nodding. Yawning and nodding. Okay, so that's what I'm saying here is based upon this relationship here and the fact that we increased the temperature, it drove the equilibrium back this direction and changed the K. We didn't cover that in the lecture because I didn't have time to show you the video. The video is posted along with the lecture. So if you want to review that. And the point that was made in that one place where the temperature was considered is that temperature changes affect the equilibrium constant. That's why Le Chatelier's moves one way or the other, depending on endothermic or exothermic. So in this case, since K gets smaller, that means these two have to get smaller. And the only way they can get smaller with an increase in temperature is if heat factor is on this side. Okay. All right, so that means the answer is B. Excuse me. No, wait a minute. At a higher temperature, K equals 1.8 times 10 to the minus 5. Thus, lowering the temperature.
After you place the equilibrium in the mixture, that in an ice bath. So
Oh,
that's gonna make B big again.
I'm having a bad day. So this is at a higher temperature, but when we
Put it in an ice bath again, thus lowering it.
we're removing heat, right?
Yeah.
So yeah, it is exothermic, and when we remove the heat, it drives it back to the right. Okay, I just missed a step. And by incorporating the ice bath,
The trick question. So like,
yeah, B will increase under those conditions. Yeah. Do we need to go through that again, or did you see my mistake? Okay. I just left out a step.
yeah, you're gonna make a mistake.
It was good as far as it went. It just didn't go far enough.
Yeah.
Okay, how about pressure? If we raise the pressure by lowering the volume of the container, well, let's see, we've got 1 mole here and 2 moles there. That means 3 moles on this side and 2 moles on this side. Right, so at equilibrium, if we increase the pressure, the fewer moles are going to be favored. So it'll move to the left and produce A. A to increase. Okay. That was the easy one. Okay. All right. Did I ask you guys already if you watch, if you've ever seen the Stargate SG-1 series?
Thanks,
There was one episode. It was in the future. And the team had to go back to the old Cheyenne Mountain complex, only now it was a museum. And they had the guides walking people through, and they were taking pictures and everything. And there was this irritating guide says, and we're walking. You gotta watch it. And we're going to the next question. All right, so now we're number 8. All right. Which statement below describes change that the system will undergo if hydrochloric acid is added? All right, so we've got a complex ion here, and we haven't studied those yet, but take my word for it. If I can just write it correctly. H2O. And we got 6 of those. Complex of this cobalt with a 2+ charge. And this has to be an aqueous solution. I mean, it doesn't say it there, but it is. And this is in equilibrium with cobalt chloride, a different complex ion, and then 6 waters are released. Okay. All right. So if this is at equilibrium and this species is pink and this one is blue, when cobalt-2 chloride is added to pure water, CO2 plus ions hydrate. They form this complex right here. The hydrated form then reacts with chloride to set up an equilibrium that produces this one. So we've got an equilibrium between these 2 complex ions. That was pink and that was blue. Now, you remember the desiccators that we've used with dryerite at the bottom, right? It's supposed to be blue, right? That means it's activated and it's absorbing water. That's the blue. There's the dryerite itself is calcium sulfate, okay, like this. Anhydrous, solid. When it absorbs water, it becomes gypsum with 2 waters associated. So we just add a little bit of this cobalt-2 plus ion in there with the chloride. You'll probably add this, just a little bit, because it's a very strong blue color. And as long as calcium sulfate is in this form, that stays blue, because this is picking up all the water and there's no water left over to make the change, to force it this direction. Okay. But when this becomes saturated and all the calcium sulfate has been turned into gypsum, we've got extra water floating around. And it combines with this one to make that one, and it turns pink. And then you know your dryerite is exhausted and needs to be reconstituted. Just stick it in the oven and eat it. Okay, so that's the reaction that's responsible for that color change in your desiccator. All right, but that doesn't answer the question. Which statement below describes the change that the system will undergo if hydrochloric acid is added? All right, so where would hydrochloric acid in? This is referencing a coupled reaction, right? We did a coupled reaction already with the dryerite, but this coupled reaction adds hydrochloric acid, right? And hydrochloric acid in aqueous solution is going to dissociate into hydrogen ions and chloride ions, right? So where does it enter into that equation? Right here. You're adding those chlorides, so you're going to force the equilibrium to the right. It becomes more blue. And so A is true, right? B is false, because it's not going to become more pink. The equilibrium will shift to the right. C is true, right? And D is false. That means E, 2 of these is true. Okay. All right, that was. Hey, do I need any more? Let me scroll down and see. No, it's a different reaction. Okay. Number 9. This is based upon 2 hydrogens plus a diatomic gas of some kind in equilibrium with H2X gas plus energy. Okay, so that's an exothermic reaction. Addition of X2 to a system described by the above equation. If we add some of this, what will happen to the others? Well, hydrogen gas will decrease. This compound will increase and will produce heat. So where does that fit in? H2 will decrease. Okay, A is true. X2 will decrease. Now, if we add X2, then the amount that we add will decrease, but the overall amount will increase because it'll only use up part of the X2 that we add in order to reestablish equilibrium. But X2 overall will increase. Right? So B is false. How about C? Will cause H2, X2 to decrease. No, that's false. It's going to increase. Doesn't say anything. Have no effect. Well, that's false. And impossible, cannot possibly be carried out. I was searching for an E. That seemed to be the only available answer. All right, so A is the answer to 9. I'm doing eating up time. Let's get moving here. Which of the following statements is true for number 11? When 2 opposing processes are proceeding at identical rates, the system is at equilibrium. That's a statement of chemical equilibrium right there in one sentence. Now, none of the above statements is true. Right? E can't be true. So that means we found our answer. We could look at the others, like catalysts are an effective means of changing the position of equilibrium. No, catalysts only speed it up. Right? That's the kinetic part of the diagram. Concentration of products equals that of reactants that is constant at equilibrium. They don't have to be equal. No, it could favor reactants or it could favor products. Depends on the reaction. An endothermic reaction shifts toward reactants when heat is added. No, if delta H is on this side of the equation to make products, then when you add heat, it's going to shift to the right, not to the left. It's not going to make more reactants. Okay, so we did find our answer. A is the only one that's true. 12. Let me scroll just a hair. Get that one on screen. Okay, consider this one. Can I write this one all right? A, B, C, and D. Well, A, B, C, D. They're all gases, correct? All right. You have gases, and these are all at equilibrium. Upon adding gas A, the value of K, what? That's a trick question, I think. The value of K does not change as long as the temperature is constant. It's just another way of approaching an earlier question. Psychologists do this all the time. Have you ever taken one of those psychology tests, personality tests?
Okay.
Yeah. I'm supposed to be sanguine melancholy. But when you take those tests, you get this question and then you get another question. And I said, wait a minute, didn't I already answer that one? They're asking it in a different way. as a check on your above answer. Right? And they factor those in to get an accurate representation of your personality in this case. So that's the same question asked in a different way. K does not change unless you change the temperature. All right, we got some repetition there. Let's go down to this one. 17. Oh, we get to play with Haber now. So we've got nitrogen gas plus hydrogen gas yields ammonia. Okay. And the delta H for this reaction is, I'm just going to put it in here like that. It's exothermic, so it's going to be on this side of the equation. Kilojoules at 25 degrees. And the K then at that temperature is equal to 4 times 10 to the 8. Okay, so at low temperature, the ammonia, the product is favored. Right? The problem is, how long is it going to take it to get there? Probably a very long time. That's why Haber had to increase the temperature, try to get the kinetics moving. Only when he did that, he changed this from a positive power of 10 to a negative power of 10. Ran it the other direction because of that value. All right, so that being said, what does this thing want us to do? When the temperature of the reaction is increased to 500 degrees. So we're increasing the temperature to 500 degrees Celsius. Which of the following is true? Okay, I think I partially answered it already. When you increase the temperature on an exothermic reaction, you drive the equilibrium to the left. Right? So that means the product of the numerator is going to decrease and the denominator is going to increase. So the value of K here is probably going to be much, see that's 1, this is 2. It's going to be much, much less than 1. You know, we have any up here that answer that. K for the reaction would be larger. No, it'll be a lot smaller. At equilibrium, more ammonia is present at 500 than 25. Nope, sorry. It's going the wrong direction. Product formation at equilibrium is not favored as the temperature is raised. That is true. C is definitely true. D, the reaction nitrogen with hydrogen to form ammonia is endothermic. False. Exothermic. All right, so C is our answer. Mm, 17 and 20. Okay. The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. So mercury 2 oxide is a solid. It's kind of a red color. You can probably get videos on YouTube that'll show you this reaction. And then it's in equilibrium with mercury liquid, which is a metal. It's going to be shiny. Maybe, depending on how much you have in there, a little bead of that stuff in the bottom. And then oxygen gas is in the headspace above all this solids and liquids. These two are on the bottom of the container. And then delta H is 43.4 kilojoules. So this is endothermic reaction. 43.4 kilocalories. All right, we didn't talk. Did we mention kilo? That was thermal chemistry last semester. What a calorie was. Okay. Right? That's a chemical calorie. Well, actually, a kilocalorie is a big calorie. Right? When you see calories on your product labels, food in the store, that's what they're talking about. Kilocalories is a big calorie that references your food product. The mass of HGO in the bulb could be increased by. Okay. We want to increase this one. What would we have to do? Well, if it's endothermic, cool it down. Remove the heat because the heat factor is over here. So you decrease the temperature, it's going to move it back to this one. Is that one of our options? Now, D is increasing the temperature, that's false. All right, A is removing some of this. If you remove some mercury, you're going to have less of that. Right? So that can't be it. Reduce the volume of the bulb. Okay, increase the pressure, reduce the volume of the bulb. You've only got one gas in here. So it's 1 mole versus no moles. So it's obvious. If you increase the pressure by decreasing the volume, you're going to drive it back over here. So if that would work, B, reduce the volume of the bulb. B would work. Mass ratio would be increased. Increase this. If we add more mercury, would that affect the equilibrium? Right. What's the K? That's it. This is a pure liquid. This is a solid. They're not part of the equilibrium. So changing the amount of this one or changing the amount of that one has no effect on the equilibrium. You can only affect the equilibrium from that factor or from the temperature. Okay, I think that was the reason I picked this question. Because your instinct would be, sure, it would drive it back to the left. That's when you get the buzzer. All right. 20. Who's next? 21 and 22. I'm gonna have to wait on that one. Okay, 21 at 500K. So we got a temperature here at 500K. 1 mole of gaseous ONCl. ONCl. 1 mole of that is placed in a 1 liter container, right? So 1 mole in 1 liter is 1 molar. 1 molar concentration. At equilibrium, it's 5.3% dissociated, according to this balanced equation. Right? So we have 2 of these. Makes 2 NOs plus chlorine. Right. These are all gases. So we consider these. This is the initial condition. Got that, get none of that, got none of that. Okay. So I can see from the answers that are given, we're going to have to do some calculations. Okay. So what we need to know is determine the equilibrium constant. That's our question. What's this? Well, what it's equal to is NO squared and Cl2, first power, and then ONCl to the second power. So I'm thinking this compound right here, the way it's written, puts N in the middle, oxygen over here, and chlorine over there. And then we got to finish up the Lewis dot structure, but they would be in that order. Okay, so that's what we're after, this right here. So what kind of change are we experiencing, and then what's the equilibrium? Because we need to know the equilibrium in order to calculate the K. Right, we're told that it's 5.3% dissociated. Right, so 5.3%
of that amount disappears. Right. So we're going to lose 5.3% of 1 is what? 0.053 molar, isn't it? Yeah, the decimal fraction of 5.3% is 0.053, right? 1, 2. Okay, so 0.053 is what we're losing here. There we go. So that means if the ratio here is 2 to 2, so that the exact same amount is going to show up over here. But only half of it shows up as chlorine because of the stoichiometry. So what's half 0.053? Let's say 0.265. Yeah. Okay, so that's there. So now we have 0.0265. We have 0.053, and let's say 749. Does that add 1? Yeah. Okay. So there are our values. We just plug them into our expression, and we have NO 0.053 squared, and then 0.0265 to the first power, and then 0.947 squared. Okay, let's see if I can do this without messing it up. 0.053, square that one, 0.0265 times that, 0.947, square that one, and divide it into that product. So I get 8.3, yeah, two significant figures, times 10 to the minus 5. That's A. All right, 22. Go. Okay. For the reaction below, Kp, they're using partial pressures for this one, equals 1.16 at 800 degrees. So we've got calcium carbonate, solid, is decomposing into calcium oxide plus carbon dioxide, gas. All right. Where's that reaction come from? Yeah, it is. It's a huge industry. Cement. Right? You just grind up limestone, run it through a hot kiln, drives off the CO2, and you're left behind with lime. And then you mix it with sand and other aggregates, and you get concrete cement, as opposed to asphalt cement. Those are the two road beds. Right. Does anybody have to come through that section up here that they got blocked off with only one lane? Yeah, they're laying down. You see how much asphalt they're putting down? That much after they reconditioned the road bed. And I've never seen them do that before. You see how they reconditioned the road bed?
Got all that stuff. I know that.
Some places they did. They actually excavated out because the foundation was bad. So they excavated it out and reestablished a firm foundation. But other parts, they just took this machine through there with hardened chisels and just pounded it into chunks. Then they ran a compactor over it, flattened it out, laid the asphalt right on top of that. Okay, back to the problem. So the Kp for this reaction is 1.16 at 800 degrees C. Okay. If 31.1 gram sample of calcium carbonate, 31.3 grams, excuse me, 3 gram sample is put into a 10 liter container. So the volume is 10 liters.
and heated to 800 degrees, what percent of calcium carbonate will react to reach equilibrium? All right. So what factors are we going to include in our equilibrium? Right. That's the stoichiometry is correct. One calcium, CO2, and then an extra oxygen there. Okay. The only part of the equilibrium is this one, CO2. Actually, that's not right either. Using the proper convention, it's partial pressure of CO2 is equal to 1.16 atmospheres. Okay. All right. So what does that mean for the reaction? Well, at equilibrium, what will be the partial pressure of CO2? 1.16 atmospheres, right? 1.16 atmospheres. What's the volume? This is the pressure. Volume is 10 liters. Pressure, volume, moles, and temperature. And temperature is 800 plus 273, right? You give us K. See where I'm going with this? Ideal gas equation. So we can solve for N. All we need is dB equals nRT. Solve for moles equals PV over RT. And pressure is 1.16 atmospheres, volume is 10 liters. What's R? With atmospheres in it, 0.08206 liter atmospheres per mole K. And then the K is 1073. Okay. So the number of moles, we'll do that one first. Let's see, 11.6, because I multiplied that one in my head. Oops, that's put it in right. 11.6, enter. And then 0.08206 divided into that, and then 1073 divided into that. And that means we have 0.1317 moles of CO2. Okay. So how much calcium carbonate? Let's see. What percent of calcium carbonate will react? How much of that did we actually use? Well, if it's 0.1317 moles of CO2, right? CO2, calcium carbonate. We really didn't need to do this because it's 1:1. The same number of moles used from this side. So it's 0.1317 moles of calcium carbonate used. How many grams is that? Well, what do we need? Moles on the bottom, grams on the top, which means lower mass. So calcium is about 40.08, let's be precise, 40.08 accurate, I should say. And carbon is 12.01 added. I'm not writing this up, or I should write it up here. 40.08, 12.01 for the carbon, and 3 times 16 for the oxygen, which is 48. So I get 100.09. So that gives us how many grams of calcium carbonate were consumed in the reaction. And let's see, 0.1317. So we used up 13.18 grams of calcium carbonate. What percent will react? So what percent does that represent? This is what reacted. What percent of the total was that? Divide by 31.3 times 100, right? It's a percentage of what we started with.
And let's see, that's 42. 42.1%. B. Okay. Never thought you'd have to use the gas equation again, did you? That's probably why I put this one in there. Yeah. Chemistry is a cumulative science. What you learn one day, don't forget, you may need it. Okay, that was 22. 24. More. Let's see how many more I got to go.
Is it gonna be a long lab today?
It's got lots of steps, right? I'll try to finish early enough so we can talk about it a little bit.
All right, he says an informal one, right?
Yes.
So we just turn it on a paper or something?
Uh-huh. Yeah. Nitrogen gas reacts with hydrogen to form ammonia. Where have I seen that one before? Reacts with hydrogen gas to form ammonia gas. Three of those. At 200 degrees in a closed container, temperature equals 200 degrees C. In a closed container, 1 atmosphere of nitrogen gas is mixed. So this has 1.0 atmospheres. Is mixed with 2 atmospheres of hydrogen. Okay. At equilibrium, the total pressure is 2.2 atmospheres. Let's see. Okay, so this is initial change equilibrium. And we know that we're told that the total, right, this one plus this one plus this one equals 2.2 atmospheres. Okay. See, is that everything I'm given? Calculate the partial pressure of hydrogen. So this is the one we want. What's the partial pressure of hydrogen at equilibrium? All right. This is 0 to begin with, isn't it? Yep. All right, we're not given the K value, but we are given this. Let me write that a little better. All right, so what's going to happen? Well, if the initial amount is 1 atmosphere and 2 atmospheres, then what's the change going to be? It's going to move to the right, correct? So we're going to have some over here, show up over there, and we're going to lose half of that over here. I'll tell you what, we're looking for X. Let's choose our X more prudently. We're going to lose some of this one, X. And that means we need to pick a different variable here, Y. Okay, we're going to lose some of this. All right, so how much of that is going to show up over here? Well, the ratio is 3 to 2. So for every 3 of those, you get 2 of those. Let's look at it this way. How would we change X hydrogen to so many moles of ammonia? Right? It would be 2 here and 3 here. So 2/3 of that is going to show up over here. Correct? All right. So if that's 2/3 over here, well, and this is, we're losing an X over here, we're only losing 1/3 of an X here. Okay? Because the ratio is for every one of these, 3 of those. So if this represents 3, that represents 1/3 of that. So far, so good? Okay. So here we have 1.0 minus x over 3. And this is 2.0 minus x over here. And this is 2/3 x. And all of these added together equals that value. So notice what we've got. We've got an equation we want to know. You'll need to know k. We just need to resolve that equation. Okay? So we get all of our x's on one side. So this x, and that x equals what? Let's see. A negative third of an x and 2/3 plus 2/3 of an x is a 1/3 of an x, right? So we got 1/3 of an x from those, and then we have a negative x here. All right, so if that's, what's that in thirds? That's 3/3 x. So it's a negative 2/3 x. So the x's are a negative 2/3. Did I lose anybody? Okay. Negative 2/3 x on this side. This is a 1, that's a 2, which means a 3 equals 2.2. And so now we have minus 2/3 x equals 2.2 minus 3, which is negative 0.8. Both sides are negative, so we can just say 2/3 x equals 0.08, right? Oh, 0.8, excuse me. There we go. Okay, so x is equal to what? 3 times 0.8 is 2.4. Right? 3, take the denominator, put it over here in the numerator, is 2.4, and then divided by 2 is 1.2. Correct? Am I losing it? Because I'm not using the calculator. Well, I'm not using that calculator, I'm using this calculator. Okay, so that's x. Right? So if this is 1.2, then 2 minus 1.2 is 0.8, correct? Atmospheres. So B is the answer.
Hey, Dr. Bush.
Yeah.
She texted me, she had to go to her car, she wasn't feeling good.
She's got severe allergies.
She's she good? Yeah, I texted her, I asked her if she was okay, she said she's okay.
Okay.
Okay, because I was a little worried, she'd never gone that long, it was kind of concerning.
Yeah, she gave me forewarning at the beginning of class.
Okay.
Said her allergies might kick in.
But how many again?
Yeah.
She's got allergies and I've got another sty.
Oh.
I had one over here that made a pus pocket. It went away. About 2 weeks later, another one kicked in. Somebody told me that if you take baby shampoo and every day massage your eyes with it, it'll keep them cleaned out and they won't get infected. I don't know.
It's not work to do every day though.
Yeah.
I won't be able to remember that.
Okay, 25. Let's see, here we go. Initially, 2 moles of nitrogen and 4 moles of H2 were added to a 1 liter container. Okay, so we're back to the same equation. Let's write it in a familiar form like this instead of that backwards way. Okay, 2 moles of nitrogen and 4 moles of hydrogen in a 1 liter container. So initially we do have 2 molar and 4 molar. Okay, and nothing there. The equilibrium concentration of ammonia equals 0.55. We got a change, we got an equilibrium. 0.55 molar is there at 700 degrees. See? See, the value of K at 700 for the formation of ammonia is what? Okay, so we've got to calculate K, which will be ammonia squared, and then nitrogen. And this is going to be in molar concentrations, not partial pressures, to the first power, and then hydrogen to the third. Go. Okay, so that's everything the problem has given us. Now, can we calculate K? Well, what's the change going to be? It's going to go to the right, correct? Because that's 0. So, but we know that ammonia is this concentration. So that means, right? It had to be that. Okay, so what's this value going to be? It's a minus and this one's a minus. Right, so this one's going to be half of that. 0.275. Yeah, is that right? 275, that's right. And this one's going to be 3 times this one. That's a 0. Oh, excuse me. 3 times that. 1 21 is 22. 2 and 6 is 8. Right, that's 3 times, correct? Okay, so that means, let me check this out. I don't trust. 0.55. Three times 2 5. Yeah, that was right. And then 1/3 of that one would be this one. Okay. Now I need to subtract this one from 2, which is 1.725. And subtract this one from 4. There we go. Now we have our concentrations at equilibrium. And we can just plug them in the equation. Ammonia is going to be 0.55 squared. Nitrogen is going to be 1.725. The first power, and hydrogen is 3.175 cubed. Okay, so let's see. I'm going to go ahead and cube this one, and then multiply by that one, and then I'm going to take this one and square it, and then divide that one into. So I get 5.2 significant figures. 5.5 times 10 to the minus 3. C. Okay. Did I lose anybody? Okay. That's 25. 26. Scroll up and catch that one. Okay. I'll have to scroll to catch E. Let's get the guts of the equation up here first. Given the equilibrium constants for the following reactions. Looks like we're going to combine 2 to make a final equation. So we have 4 coppers and oxygen yields 2 Cu2O solid and has an equilibrium of K1. Right. And K1 references which one? That one right there. Okay, then the second one is 2 CuO solid yields Cu2O solid plus 1/2 O2 gas. And this one has a K2. All right. So our target is this one, 2Cu solid plus O2 gas yields 2Cu solid. And we want to know how would we combine these to get the K for that equation right there, the K for that reaction. All right. So we need a little refresher on Hess's law, right? How do we combine these two to make that one? Well, let's see. We need 2 coppers down here, but we got 4 up there. Right. So what if we take half of that equation? Right, that would make 2Cu plus 1/2 O2 and Cu2O. What would that do to the K? When you multiply by a factor, the factor becomes the power of K to make the new K. So the new K would be K1 to the 1/2 power. Right? Okay, so that gives us this one here and here. We need CuO on the other side. So we got to flip the equation. Cu2O solid yields, put down the opposite, plus 1/2 O2 gas yields 2CuO solid, right? So that gives us this one down here from there. See, we're going to use this one and this one. But what does that do to the K? We flip the K. I mean, we flip the equation, which does what to the K? It inverts the K. Right? So it's K to the -1. Correct? That's the same thing as 1 over K. Okay. How about oxygen? Well, we got this half and this half. There we go. Now, what about the others? Cu2O, Cu2O. That one cancels, and that one cancels. Leaves this one, leaves that one, this one, and that one. Okay, we're good. So now what do we do with this one and this one to get the KEQ for our new equation? What do you do to the K's? Multiply them. Multiply the K's. So we've got K1 to the 1/2 times K2 to the -1. Now, maybe that's not up there, but let's see. Let's see. Where do we have K1 to the 1/2? B? Excuse me, I need to. Yep. So this one stays in the numerator. Yeah, B has 1 and E has 1, but K2 is in the wrong place. Right, this is in the denominator because it's to the -1 power. So that means we could also write it like this. Like that. Put it in the denominator. So there's your answer. E. Okay. The whole purpose of that one. And see if you remember the rules. That's basically it. And let's see, here's another one. Okay, 28. Exactly 1 mole of dinitrogen tetroxide is placed in an empty 1 liter container and is allowed to reach equilibrium by this equation. So N2O4 gas in equilibrium with two NO2 gas. Yeah. And we've got 1 mole in 1 liter. So initially we have 1 molar and we have none of that. Okay, so we're going to have a change, and at equilibrium, we're going to do this and this. So what is it asking for? What's the value of the equilibrium constant in terms of molarity? Okay, so we are looking for KEQ for this one, which would be NO2 squared over N2O4, the first power. Right. We're also told what else? At equilibrium, N2O4 is 37% dissociated. So it's 37% of 1.
37.
Minus. So we're going to add how much over here? 0.63. 64?
10 plus 3 is 0.
2 times this, 1 of those, and 2 of these.
You're at 1.1.
Oh. Right. Got to carry the 1.
Wouldn't it be 6.3?
Well, if the change, if you're losing 0.37 over here,
You're gaining 0.63.
you're gaining twice as much over here.
Twice as much, okay.
Yeah. So we both made a mistake.
Yeah.
It balances out. Okay. So at equilibrium, we have this one, and this one would be 3, 6. Oh, that's the one you were thinking of right here.
Yeah, that's fine.
Yeah, I was thinking this one and you were thinking that one. Okay, so that's good. Now we can calculate our K. Right. 0.74 squared over 0.63 equals what? 0.74 squared. And then divide by 0.63. So I get, let's see, they use standard notation, so I'm going to read it that way. 0.87 E. Right. 29. Consider the reaction. Hydrogen plus iodine plus is 2HI. We did that before. Hydrogen, it doesn't tell us that that's the gas, but it is. And this is a solid. 2H, which is also a gas. For which K is 44.8 at a high temperature. Right, so at a very high temperature, that one is favored. The product is favored. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, determine the equilibrium concentration of hydrogen. Okay. An equimolar mixture of reactants. So we've got the same amount here as here, and nothing there. Right? That's the initial conditions. Right, so we know the change is going to go that way. Concentration of the product is 0.5 molar. 0.5 molar. So that means this had to be 0.5 molar there. And this had to lose half of that, right? Because it's 2 to 1. So if this is 0.5, this is 0.25 minus, and this is also minus 0.2. Okay, so x minus 0.25 and x minus 0.25 is that. The equilibrium concentration of hydrogen. So what we want is this whole value right here, isn't it? Okay. Well, you know what? This one doesn't even enter into the calculation. K, because it's a solid, K is equal to HI, and this is molar squared, and this is hydrogen to the first power. And that's equal to 44.8. Okay, so we don't even have to consider that one except for the stoichiometry. So actually, we can treat this as a single variable, right? We can treat that as y. So this is equal to 0.50 squared. And in the denominator, we got a y. 44.8. Did you see what I did there? Rather than bothering with this calculation here, right, the answer we want is that value. So we just assign it a new variable and plug it in the equation. Now we have an equation in one unknown. We would have before, but if we had done it this way, then we'd have to solve for x, and then we'd have to subtract 0.25 from it to find y, and why bother? Right? We can save ourselves a step.
I see what you did there.
Okay, so y is on that side, and then what 0.5 times 0.5 is what? 0.5 squared is 0.25. Let's see. Y goes over here, this goes over here, so it's 0.25 divided by 44.8. Okay. 5.6 times 10 to the minus 3. 5.6 times 10 to the minus 3 molar. Oops. What did I do wrong? Determine the equilibrium concentration. See, did I write this correctly? Squared divided by this one, 44.8. We know that this concentration is 0.5, correct? Concentration of the product is 0.5 molar. So 0.5, let me see if I did it right in my calculator. 0.5 squared. Yeah, 0.25. 0.25 here. Y goes over there to this one. Yeah, Y goes over there. 4.8 goes over here. And I got it 5.6, 44.8. 5.6, 10 minus 3. Now Y, let me see if I could have made mistakes. Oh, at high temperature. Okay, at high temperature, this is going to be a gas. That's the trick. That's a gas. So this is actually, write that better, Y. This is also Y. So the expression is still this one. Okay, so that's going to be squared. Correct? That means this is squares that one, and Y equals the square root of that value. That's where I made my mistake. It's that one little, that 2-word trick, high temperature. This is square root. There it is, 7.5 times 10 minus 2. Okay, live and learn. Except I've done this problem a dozen times before. And it caught me that time. Okay. 30. All right. So we've got 2 hydrogen fluorides are in equilibrium with hydrogen and fluorine gas. Okay, and the K equals 1 times 10 minus 2. Yeah. So, given 1 mole, 5-liter flask, 1 mole in 5 liters. If we start off with 1 mole of HF in 5 liters, that's 0.2 molar, correct? 150. 1 divided by 5. And this one is 0.362 divided by 5. That equals something. And then and fluorine is 0.75. 0 divided by 5. So this one is equal to what? And that one's equal to what? Let's go ahead and figure that. 0.362 divided by 5 is 7.24 times 10 to the minus 2. And this one is 0.75. 5 is 1.5 times 10 to the minus 1. Okay, that's initial concentration. Okay. What's the reaction quotient? All right, so we don't have to do any of this other stuff. It just wants to know what's the Q. All right, so we write Q the same way we would write K, only we use non-equilibrium values. These are both to the first power, and this one is to the second power. Correct? So this one is 7.24 times 10 to the minus 2. This is 1.50 times 10 to the minus 1 divided by 0.2. That should be Q. And let's see, multiply these together. Yes. So I get 5.4 times 10 to the minus 2. Oh, standard notation. Right. Closest I can get is 0.054, which would be, oops, what did I do wrong? I see it. So, 0.2 corrected measures. So that one, and then 2. Let me do it again. 7.24 exponent minus 2 here. First power, second power. 1.5 exponent. Oops. 7.24. Okay. Then 1.5 exponent. Let me just sign times. And then 0.2 squared divided by that. 0.272. Thereabouts. B. Okay. Details. Details will get you every time. It's 30. 32. The carbon disulfide and chlorine react according to the following equation. Let's see. Let's go ahead and write it. CS2 plus 3Cl2, these are both gases. Carbon disulfide yields 2Cl2, the gas, and carbon tetrachloride. Yes. When 2 point, it's an equilibrium, 2.14 moles of CS2 in a 2-liter container. So initially, we've got 2.14 in a 2-liter container, that molarity. Then this one we have 5.85 in a 2-liter container, and that molarity. Allowed to come to equilibrium, so none of this and none of that. The mixture is found to contain. So at equilibrium, the mixture is found to contain 0.620 moles of this compound in that same 2 liters. Okay? How many moles of CO2, chlorine, are present at equilibrium? All right. So let's calculate these values first. Let's 2 divided into 2.14 is 1.07 molar, right? And 2 into this one is 2.1925 molar. Okay. So how did we get to this one? Well, let's go ahead and divide it to 0.310 molar. So that means the change had to be plus this much. 0.310 molar. And assuming this is balanced, yeah, this had to be 0.310 molar. Right, so it would be 0.310 molar there. So how much did we lose over here in that change? Well, this one we lost exactly the same amount. 0.310 molar was lost because it's 1 to 1 to 1. But this one is 3 times as much of that was lost from here. Correct? Because of the stoichiometry. 3 of these, if we had add that much over here, we lost 3 times that much over here. No, that's not looking too good. Oh, no, it is. Okay. What's 0.310 times 3? 0.930. So we lost that much. Correct? And the question is, how many moles of CO2 are present at equilibrium? So we just subtract this one from that one. And I get 1.995, or about 200. Well, that's not right. Why is that not right? What did I do wrong? Nobody's going to tell me, right? .93. That's good. And 1.07, that's right. How did I get 3.99 out of that? Oh, it's too simple.
Computers have to do it.
This is molarity. This is concentration. The question is how many moles, right? So it's times 2 liters, about 4 moles. Yeah, that's exactly right. I couldn't see the forest for the trees. Okay, everybody good? Okay, after I get over my whiplash. We'll move on to the next one. All right, 33. Should be nearing the end. Okay, 3 more, including this one. All right, minus 80 degrees. Degree C for the reaction. Okay, N2O4 to NO2. Okay. The K is 4.6 times 10 to the minus 8. So reactants are heavily favored. We introduced 0.047 moles of N2O4 in a 1 liter container and let the equilibrium establish. The total pressure in the system at equilibrium will be. All right. So initially, we're going to put 0.047 moles, 0.047 moles in 1 liter. So it's that many moles. Okay. And we have none of this. So the change, we're given anything else? No. Okay. So the change, we're going to lose some of this and gain some of that. So if we lose this much, we're going to gain that much. All right. So at equilibrium, we got 0.047 minus X, and then we have 2X here. Now let me see. This is the molarity, but it's in 1 liter. So this is also the number of moles. Well, let's just set it up. Okay, so the equation then is going to be 4.66 times 10 to the minus 8 equals this one squared divided by this one to the first power. Okay. Okay. I was thinking we could throw this X out because it's gonna be so small. I bet it would work too. Okay. Because you're gonna subtract, X from here. What is X compared to that? Well, we actually don't. It's gonna be really small. Let's go ahead and do it. Like, so 4.66 times 10 to the minus 8 times 0.047. Point oh four seven. So that's 2.1902 times 10 to the minus 9. These two, and then minus X would be 4.66 times 10 to the minus 8. X equals 4x squared, correct? All right, let's throw that X out. Otherwise, we're going to have to solve the quadratic, correct? Let's throw the X out. It's going to be so small, so very small, 10 to the minus 8. We're going to lose very little of that X. So we can throw this term out. Minus X times that would be this term right here. So now we've got this equal to 4x squared. Divide this one by 4. And then take the square root of it, right? I'll throw this step back in here. 4, that's 10 minus 10. X squared. So X would be equal to square root of it. 2.34 times 10 to the minus 5 molar. That's X. That's X here. So this is going to be 2 times X would be this one, 4.68 times 10 to the minus 5 molar. And this is going to be 0.047 minus X, which is essentially 0.047. All right. Now here's where you have to back up and take a look at it. If this is the molarity of the reactants, and this is the molarity of the products, what's the total moles in there? If this is molarity, it's a 1 liter flask, so this is going to be 0.047 moles, right? And this is going to be that times 10 to the minus 5 moles. How is that going to change this one? It won't. Right? 10 to the minus 5th, and this is 10 to the minus 2. That's 3 orders of magnitude smaller. So add those two together to get the total number of moles, because that's how we're going to calculate pressure. We need the total number of moles of gas. This is really the only factor we need. Oops. We're looking for pressure. Okay. Pressure equals nRT over V. So the number of moles is 0.047, 0.08206 for the R value. And what's this one? 273 minus 80. 193. Okay. Divided by volume, 1 liter. All right, so I've got the K in there. I'm going to multiply it times R, and then times the number of moles of gas by 1. So I get pressure is equal to 0.744 atmospheres. B. Okay. So we used a couple of tricks. One, we said that that's too small to be a problem. That X is too small to be a problem. Plus, if it's really that small, then this value is not going to change that value enough to affect the pressure. So in the end, we just used that many moles. Okay? It could save you a lot of time on a test. 34. A sample of solid ammonium nitrate placed in an evacuated container and then heated so it decomposed explosively according to the following equation. At equilibrium, the total pressure in the container was found to be 2.63 atmospheres at a temperature, of 500 degrees. Calculate the KP. All right. So ammonium nitrate is a solid. N2O there plus 2H2O. Yes. At equilibrium, the total pressure is 2.63. So I'm just going to write this up here to help me. And we only need to add these two if we're calculating pressures. Is 2.63 atmospheres. The total pressure of this one plus that one. Because that's a solid, it may not even be there. It might have all decomposed. And the temperature is 500 degrees. All right. Calculate the KP. So the KP is going to be partial pressure of N2O times partial pressure of water squared. All right. So when this thing decomposes, we've got a certain amount here. Didn't say how much, did it? No, it didn't say how much. So we've got a certain amount here, and it's going to produce a change here where we get some there and some there, and then whatever we subtract here. All right. So we're going to get so many moles here, and we're going to get twice that many moles here, correct? No arguments. Okay. So we're going to have an X here, and we're going to have a 2X there. And these are the only terms that go into that equation. Correct? Based on the stoichiometry. You're going to get one of these, and you're going to get two of those from the decomposition. And the total pressure is here. Right? So what's X? We've got an equation in one unknown. Right? 3X equals 2.63. So X equals what? Divided by 3 equals 0.877. 877. Yeah, we can say atmospheres. Right? The ratio is going to be the same because this is an atmosphere, so this is an atmosphere. So we got that X and 2X equals 1.753 atmospheres. Okay. Now we've got our values that we can put into this equation. Partial pressure of N2 is X atmospheres. Partial pressure of water is 1.753 squared. So I'm going to go ahead and square that one since it's already in here, and then I'm going to say 0.877 times that, and I get 2.70. Okay. All right. I think there's just one more. That I hadn't marked. $36.
I can do this and quickly, it'll leave us a little time. At a certain temperature, K for this reaction, 2NO2.
Okay, this is that reaction only backwards. Is 7.5 K. Let's see, this is at a certain temperature, K for this reaction, gas equals 7.5. Now they give us the units of measure, but we don't need it. Right, and this is equal to N2O4 divided by NO2 squared. Okay. If 2 moles of NO2 initially, 2 moles in 2 liters is 1.0 molar.
What's the concentration of N2O4 at equilibrium?
Okay. There's a change, there's an equilibrium. Go. So we want to know how much this is. Correct? Because
That's the concentration of N2O4 at equilibrium.
so that means for every one of these, 2 of those disappear. Right? So 1 minus 2x is this value and that value. So 7.5 equals N2O4, which is x, divided by 1.0 minus 2x squared.
Okay, let's ask ourselves, how big is X? The value is 7.5, so it's going to be to the right, correct? That means X is going to be a substantial amount. And we can't throw it out. It's too big. So we're going to have to solve this quadratic equation.
All right. So let's expand this quadratic. Right? 1 times 1 is 1. Minus 2x times minus 2x is minus 4x squared. Then minus 2x times 1 is minus 2x, and then minus 2x times 1, minus 2x, or minus 4x.
Okay? Expanded the polynomial, correct?
All right. So now we got to add this one in. We got to have 0 on one side. So 0 equals 7.5. Let's put it in
ABC order.
So the x squared term comes first, minus 4x squared. Then the x term comes next. Oop, we got an x up here. Hold on a second. This has to come over here. 7.5 times minus 4x squared minus 4x plus 1 equals x. So far, so good. I took this expanded polynomial, multiply it times that one. That's equal to x.
So I'm going to use my calculator for the rest. 7.5 times 4 is 30. Minus 30 x squared, these two terms. And 7.5 times minus 4 is minus 30 x. And then plus 7.5 equals x. So now we bring this x over here, it becomes a negative. That's minus 31x plus 7.5. And then minus 30x squared. Okay? Now we need our quadratic equation right here. This is the A term, this is the B term, this is the C term. So x equals minus b. Minus of minus 31 is plus 31. Plus or minus square root of b squared
minus 31 squared minus 4 times A, which is minus 30, times C, which is 7.5. Okay? Then all over 2A. So 2 times minus 30. Okay? All right. So let's do this part right here and find out what that's equal to. Let's see, 31 squared. And then 4 enter and 7.5 times and 30 times. And this is a positive because that's a negative and that's a negative. So this term up here is going to be 1.861 times 10 to the third. Let me check this up again. 31, I'm going to square it. And then I'm going to take 4 enter 30 times, 7.5 times, and add that. Yes. Okay. So now the square root of this is what? Square root of that is 43.14. So that's all this term right here, and it's either plus or minus. So the first possibility is 31 plus 43.14 divided by a minus 60. Right? We can throw that one out, right? Why? Because we can't have negative concentrations. Right. All right, so that one's gone. Now let's make this one a negative. Right? So, or 31 minus 43.14 divided by minus 60. Okay. So let me change the sign on that and add 31 and then 60 divided. So that gives us 0.202. And that's X. So let's go back to the question. What's the concentration of N2O4? It's 1 minus 2X. Right, so 2 times that, this one has to be in. Right? It couldn't be the other one. 2 times that, and subtract that from 1 is this right here is 0.594 molar. Right? Where did I mess up? Did I make it harder than it should have been? Let's see, 30x squared minus 31, 7.5. Okay, so I got the quadratic right. Then I had to solve the quadratic. 31 plus or minus 31 squared, 437.5. All right, divided by 60. Okay. A. Now, A is a negative, so that needs to be a negative down here. Minus 294. All right, we made that one correct. But I ended up here with, if that's X in molarity, then 2 times that. And subtract from 1. It's 594. It says it's 0.39. How does it get 0.39? I think Oh, how did I choose my X? N204. Oh. What's the question? What's the concentration of N204? It should be X. But I'm still wrong. Because X is this value. Right? So where did my calculations go wrong? It had to be in the solution of this equation right here. 31 squared. I got that. Now 4 enter 30 times 7.5 times that one. That's plus 126 and 30, the square root of that. 43.14. Okay, that's right. And that's, we can't use this one. We have to use the minus one. So 31 minus this minus 12.14 divided by 60. I still get that value. Am I missing a square somewhere? It looks right. Because we picked the X right. Because the X is our answer. We didn't have anything in there already, did we? Moles of NO2 are placed. Calculate the concentration. That's the concentration there. All right, so I'm not sure. I get that value, but that's not one of them. It's none of these. Any ideas? No? Hey, we're good up to here. We're good up to that point. Wait a second. Is this right? First of all, this one. 1.0 minus 2x squared. Yeah. Then x. Yes. Is equal to 7.5. And expand this one. So this one is 4x squared. There it is right there. Yep, that's it. So this is plus 30. Plus 30. That's negative. Let's see, does that affect the rest of it? 7.5, 4x squared minus 4x plus 1. Okay. 7.5, 5, 5. And this is that's 1x. Okay. So this is correct. And this one needs to be, that's right. This is B. And this is positive. Okay. So this one is 4 enter 30 times 7.5 times. That's a negative. Yeah, that's negative. And then this one is 31 squared. Then we add those two together. And that's 661. That's the problem right there. 61, square root of that is 7.81. There we go. So 7.1 plus, this is still a negative.
What happened? You didn't square B?
I'm sorry?
You didn't square B? Is that where you messed up?
No, no, it's right here. 4x squared. When I squared this term, when I was expanding the polynomial, I kept the negative. And a negative times a negative is positive. So that bled all the way through to here. And 30 here, this is a positive. But this one is 31 minus 7.81. So 31 enter, 7.81 minus, and 60 divide. This one is 0.387. And then this one is negative 7.81. Wait a minute, that was negative. So that's the negative one, and this is the positive one. And this is 0.647. Okay. So how do we decide between the two? Oh. If we say 2 times this one is bigger than 1, so that gives us a negative. That can't be. So we have to use this one. That's the answer right there, 3.87. Or 0.39, excuse me. I can't let these things go. I have to figure it out. That's when you learn. It's when you struggle with something. Then it imprints it on your brain. Okay, I think that's the last one. Yeah.